In the last video we constructed this chain map gamma from C star k to C star k prime, and we want to claim that this actually induces an isomorphism in homology. I mean, remember, any chain map gives you a induced homomorphism of homology groups, and we want to claim that in the case of this gamma that's actually an isomorphism. And the way we're going to do that is we're going to recall that we've got this map mu of simplicial complexes. Remember, mu is this last vertex map. It's actually a simplicial morphism from the complex k prime to the complex k, and so it induces a chain map mu hash from C star k prime to C star k. And we want to claim that the corresponding map in homology is just inverse to what we get from gamma. And so one way, we have to do two things. We have to prove that mu hash composed with gamma is giving us the identity, and also the other way around. So on this this slide we're going to consider it this way. We do gamma first and then mu hash. We claim that's just equal to the identity on the chain group C star k. So let's just do the case of a 2 simplex first. So we've got a 2 simplex sigma as v0, v1, v2, which we're going to write with the vertices in ascending order with respect to our chosen order on all the vertices. And so that means in particular v2 is the last vertex, and mu sigma is v2. So gamma sigma, we had this before, and what we have to do is we have to take a sum over all possible permutations of 0, 1, 2. And this is what we get for the identity permutation. We introduce the 0 first, then the 1, then the 2. Give this 0 bar 0, 1 bar 0, 1, 2. So that's an element of C2k prime. And similarly, just look at this last one here. This is where we introduce 2 first, and then 1, and then 0. So that's an odd permutation of 0, 1, 2, so you got a minus sign. Okay, so here we get gamma sigma is a sum of 6 possible simplices, 6 2 simplices of the complex k prime. So now we're supposed to be looking at mu hash composed with gamma. Okay, so we apply mu hash to each of these things, and remember mu is just the last vertex map, so all that happens is that each of these terms between bars, this guy here is 0, 1, 2 bar, and that gets sent by mu to just 2. Okay. So we take the last element in each of the groups between bars, and so that gives us 0, 1, 2 for this term, then 0, 2, 2 for here, 1, 1, 2 for that term, 1, 2, 2 for that term, 2, 2, 2 for that term, and 2, 2, 2 again for the very last term. But remember, this is all happening in the group C star k, and by definition in C star k, if we've got one of these kind of, you've got a term with a list of vertices with repetitions, then that counts as 0 in C star k. So here we've got the 2 repeated, here the 1 repeated, the 2 repeated, 2 repeated, 2 repeated. So all of these terms here, they all just count as 0 in C2k. And all that's left is this 0, 1, 2. Okay, so we find that mu hash gamma sigma is just 0, 1, 2, and that was our original sigma. So we're seeing that mu hash gamma is acting as the identity on this 2 simplex. We want to claim that actually works for an arbitrary D simplex, so let's kind of go through that a bit. So we've got a typical D simplex for K. You've got a chain of vertices V0 up to VD, which we are writing again in increasing order, so that the mu of sigma hat is VD. Gamma sigma, so some of these terms form plus or minus phi sigma pi, pi running over all possible permutations of 0 up to D. We want to claim that most of these are actually just giving us 0. Okay, we look at mu hash phi sigma pi. It's going to have repetitions, like all these terms over here have repetitions, and so counts as 0 in the chain group. To see that, well, let's use the notation tor I for v pi 0 up to v pi I. Okay. Then this term that we've got here, mu hash 5 sigma pi, is mu hash of tor 0 hat up to tor d hat, which is the last vertex of tor 0 up to the last vertex of tor d. Okay. So how can this possibly be non-zero? Remember, if there's any repetitions, it's 0. So for it to be non-zero, the last thing in tor I has to be different from the last thing in tor I minus 1. Remember, and so so the last thing in tor I minus 1 is the maximum of v pi 0 up to v pi I minus 1, and then last of tor I has to be bigger than that. So it has to be not an element of tor I minus 1. Okay? And the only way that can happen right? As if these pi's are all happening in order, right? I mean, you want the last thing in tor I is going to be the maximum of pi naught and pi 1, and you don't want that to be equal to pi 0, so pi 0 has to be less than pi 1. And the last in tor 2 is going to be the maximum of pi 0, pi 1, pi 2. You don't want that to be equal to pi 0 or pi 1. So we know already pi 0 has to be less than pi 1, and then that has to be less than pi 2, and so on. So the entries in this permutation pi have to be in increasing order, but that just means the permutation has to be the identity permutation. And if the pi is the identity permutation, that just means the last element in tor I is just I, and so mu hash 5 sigma ID is equal to sigma. Okay. So this proves that for all d, we've got mu hash gamma of sigma is equal to sigma. So on the last slide, we proved that if we do gamma and then mu hash, we just get the identity map of C star k. Now we want to consider what happens if we do the composite the other way around, if we do mu hash and then we do gamma. Okay, so that's not, unfortunately, just equal to the identity on C star k prime, but it is chain homotopic to the identity. And we proved earlier that if you've got two chain maps that are chain homotopic, then they have the same effect in homology, and that's going to be the key thing that we need here. So remember what it means to say these things are chain homotopic. It means that there's going to be some map xi that increases degrees by 1 from CRK prime to CR plus 1K prime. dxi plus xid is going to be the identity minus gamma mu hash, right? The difference between the identity and this composite that we're talking about. Okay, so we're not going to give a full proof. We're going to outline the definition of this map xi, but we're not going to prove that it satisfies dxi plus xid as id minus gamma mu hash. But the definition goes like this. So we need to consider a generator of C star k prime. So it's going to be like a simplex of k prime. We're going to call theta. And so remember, that's going to have the form sigma naught hat up to sigma d hat, where the sigma i's, they're simplices of k, which are nested in order. Sigma naught contained in sigma 1 up to sigma d. So let's let vi be the last vertex of sigma I. So it's an element of sigma I in particular. And because these simplices increase, we're throwing in more and more things which might or might not increase the maximum, right? I mean, vi is the maximum element of sigma I with respect to our chosen order on the vertices. So if we make the simplices bigger and bigger, then the maximum is going to go increase. So we have v naught less than or equal to v1 up to vd. And mu hash sigma, remember the way mu hash works, we just apply mu to each of the sigma I hats in theta, and so that just gives us v0 up to vd. That might be 0 if there's any repetitions here, or it might be non-zero. Okay, these we can only assume that these vi's are weakly increasing. They might not be strictly increasing. If there are any repetitions, then this mu hash theta will be 0. Okay. So now to define xi, and xi is going to have a bunch of terms depending on some permutations. So we're going to we get a term for each choice of k between 0 up to d minus 1, and each permutation pi of 0 up to k. And to define the relevant term, we're going to let tor I be the simplex consisting of v pi naught up to v pi I, and then our psi of theta k pi is going to be this list here, tor 0 hat up to tor k hat, and then sigma k hat up to sigma d hat. Okay. So notice all these, pi is a permutation 0 up to k, so all these elements pi j, they're in the set 0 up to k, they're less than or equal to k, in other words. And v pi j, that's an element of sigma pi j, it's the last element of sigma pi j. But sigma pi j is a subset of sigma k, because pi j is less than or equal to k. So all these v pi j's, they lie in sigma k. And in particular, that tells us that this tor k is contained in sigma k. Right? Tor k is v pi 0 up to v pi k, and all those guys, they lie in sigma k. And then also it's kind of clear from the definitions, I mean, we're just throwing in an extra vertex each time. Tor naught is contained in tor 1, contained all the way up to tor k, and then tor k, as we said, is contained in sigma k, and then the sigmas were nested as we saw up here, so this is contained So we've got sigma k nested up to sigma d. So this means that this list here is this is a nested list of simplices. So if we take their barycenters, then that counts as a simplex of k prime, unless there's any repetitions, in which case we just get 0. So now it's meaningful to give this definition sigma xi of theta, the sum over all possible choices of k and all choices of pi, minus 1 to the power k times the signature of pi times this this psi theta k pi that we wrote up here. So that's a well-defined map from the groups of k prime to groups of k prime, just increasing degrees by 1. Okay. And we want to claim that if we do dxi plus xd, that's the identity minus gamma mu hash. We're not going to prove that. It's the same kind of ingredients as stuff that we've discussed already, but just a little bit more complicated. Okay, but now we can prove as a corollary that these maps gamma star and mu star on homology groups, gamma star from the homology of k to the homology of k prime, and mu star in the opposite direction, they're going to be isomorphisms inverse to each other. So to prove that, well, firstly we proved that mu hash gamma is just equal to the identity, and so because homology is a functor, that means that mu star gamma star is equal to the identity. That's from the homology of k to the homology of k. And similarly, gamma mu hash, well, that's chain homotopic to the identity, and chain homotopic maps have the same effect in homology by a fact that we proved a while ago. So gamma star mu star is the identity. So that proves that homology is invariant under subdivision.